All right, friends, we had some great questions. There's the data. There's the data. And in case you're having a hard time kind of seeing it with the, let me change the window a smidge. I want to change the, let's see, I want to make this -1, maybe up to 45, that's fine. We're going to scale that by 5s. And all this is going to do, make it -1 to 7, scale it by 1s. That just puts a more incremental number of tick marks on the axes. In case you're having a hard time seeing it, there's one there, that's 38, 0, 38, and so forth and so on. Not quite in focus yet. Well, that's as good as it's going to get. All right. So the question now is, what model defines it? What model defines it? What do you think, Ben?
Exponential.
Why exponential? What the hell is exponential?
Really? Because there is the more you go, the less you have closer it goes to.
I agree, but quadratic would also do that, wouldn't it?
Yeah.
How many of you guys saw quadratic when you saw this? Yeah. Right. It doesn't look linear. Could you get a best fit line for this?
Yes.
Yes. Watch. Stat calc. Lin reg, y1. There it is. There's the best fit line. Does that do a fairly good job of describing what's going on with the data? No. No, it's a terrible job of describing what's going on with the data. It grossly underestimates where we started. It kind of does that one okay and kind of does that one okay. And then what happens over here? It starts going negative. That doesn't make any sense. It doesn't make any sense at all to go negative. So linear doesn't make any sense. Even if you did the lin reg and then fit it, before you even did it, you realize it's not going to be linear. Gabe, what are you thinking?
How would you? So if you did the quadratic.
Let's do the quadratic now. Okay.
And it makes a parabola. How
Right.
would you fit the parabola?
Gabe's voting for. Let's go quad reg. Let's go quad reg. Hold that thought, Shirley. Hold that thought. Here we go. There's the best fit parabola. Okay. Here she is. Looks pretty sick, doesn't it? And I say sick in the East Coast good way. But what's the small problem? I think this is what Gabe is getting at when you say, how do you make it fit? What are you seeing, Gabe, that upsets you?
Well, how do you fit the line that keeps going up?
This is a problem. Because this implies that once we're down to 0, we can bring heads back in. That doesn't make any sense, does it?
Could you reverse and go everyone who got tails?
That would be the same parabola, essentially.
38.
It would essentially be the exact same. Because think about it this way, Gabe. Check this out. Gabe's got a great question. Suppose we reversed it and said number of tails versus number of heads remaining. Going back to our original data, what would that 19 be? Trick question. It would be 19. Because 19 people got heads, which means the other 19 got tails. What would that 17 be? This is not a tricky question. That'd be 21, wouldn't it? If 17 got heads, the other 21 got tails. Oh, look. What would that 21 be? 17. 20, 18. So you see, you'll get the exact same parabola because heads and tails are equally likely.
What did I do?
I don't know. It looks like you probably hit grab without running the regression. You're still using the exam question. Okay? All right. So, quadratic looks okay to a point. It looks okay to a point, but then it goofs up here. You could also check it a different way, couldn't you? You could also check it a different way. I'm gonna shut this down, fire Excel back up, and look at second differences again. Look at second differences again, okay? Because this is what you guys told me. Second differences are consistent. So, let me adjust the camera so you can see this. Okay, let's go up to here. All right. So here are first differences. First deltas. Except I spelled first wrong. S, not a D. All right. So here, this is going to be equal to this minus this. Okay, and there they are. They're the first differences right there. Okay. Not consistent, but we didn't expect them to be consistent because this isn't linear, right? But now second differences. Let's take a look at these. U equals that. Whoops. Minus that. Okay. Not consistent either. Actually, predictably inconsistent. So it doesn't fit a linear, nor does it fit a quadratic model. So now the question is, if it doesn't fit a linear or a quadratic, what does it fit? Ben's actually nailed it with exponential, but we haven't talked about that yet. So I want to take a pause from exponential just for a second, Ben, and I want to see if we can kind of figure out the relationship. Oh, I should have the averages up, actually. Let's have the averages up. What is happening as we go? Let me copy this data over here. Copy, paste. Copy, paste special values. All right. Let's focus just on this right here, okay? Just on this right here. What's the relationship as we start at 38 and then go to 20, and then we go 20 to 9, and then 9 to 4, and then 4. It's not perfect. It's not perfect, but knowing what you know about coins, what's happening? Echo, what's happening? You're losing approximately half each time. Does that make sense? Every time a bunch of us flip a coin, how many of us should get heads? About half. And then the next time, those halves should flip again, and that half should be cut in half, and it should yield a quarter. Oh goodness, hang on. Let's see if this makes sense. Okay? Let's do predicted versus actual. So here's what we actually saw right here. Let me stick a column, stick a row in here. Okay, here's actual, and here is Echo's prediction. With a capital E for name, huh? Yes? Yes. Okay, ready? So we're going to start at 38, for sure. According to the prediction, realistically, exactly how many should we have after one flip? It should be half, correct? It should be half. So this should be equals 38 times 1/2, which would be 19. Make sense? Okay. How about in the next one? What should we have?
9.5 or 10.
Say that again, Scott.
Like 9.5.
Because what are you doing?
Halving 19.
You're halving. I like that. You're halving. Equals, basically, it equals that times 0.5. And then essentially, if we can pull that down, that should be 4.75. And then that should be 2.375, and so forth, and so on, and so forth, and so on. Is it behaving?
Yes.
That's a pretty damn good fit, isn't it? That's a pretty damn good fit. So what we have to do is we have to look at this new model. I'm going to mute this for a second. We're going to come back to this. We've got this new model. And Ben, you have the correct title. This is definitely an exponential model. Okay, this guy right here. Put it back up. Turn it back on. This data right here is definitely exponential. But what makes it exponential? Is it a constant slope? Nah. Constant slope will be linear. Is it a constant second slope? Nah. What's happening constantly? Something is happening constantly. But what is happening? As x goes up by 1 each time. 1, 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. Something is happening constantly to the y values. What's happening to the y values? Be brave, my friends. Go ahead, Ben.
They get divided by 2.
Good. Or, I want to make it more general, but it's okay. They're getting multiplied by a half. And the reason I want to do it that way, rather than divide it by 2, when you think of exponentiation, when you think of the word exponent, what do you remember from previous math classes? Give me an example, something. I say exponent, you think? Times itself, right? 2 squares, 2 times 2. 3 to the 4th is 3 times 3 times 3 times 3. 27 is 3 cubed. You're thinking of a base times itself, not divided by the times. I know that division is the reciprocal of multiplication, and they're basically interchangeable. But I'll just think of multiplication. So basically, the way exponential differs from linear and quadraticness is, each successive term, y value, is a multiple, constant multiple, of the previous y term. And when I say constant multiple, we're applying the same multiplication again and again and again and again. So to get from 38 to 19, we multiplied by a half. To get from 19 to whatever this was, 11, we multiplied by a half again, which means we multiplied by a half twice on the way down. To get to the next one, we multiply by a half again. So each successive y value gets multiplied again by that constant multiple. Factor, I guess constant multiple, we could probably use the word factor. Probably is a better, or base, you use base. That's kind of a throwback term to your algebra classes. Now, let's find that guy in our TIs. Let's find that guy in our TIs. This is the last regression we'll do in here together. Last regression that we'll do together. So, when you go to your TIs, you're in the same window, the same menu, your calc menu. Keep going down until you see this guy right here, Expreg. That's exponential. That's exponential regression. Exponential regression. Looks like it's 0 on mine. I'm not sure what it is on your guys. Expreg, but you do it the exact same way. It's Expreg, stick it into Y1. Hit enter. Don't hit graph, hit enter right now. Because I want you to see, whoops. I want you to see why we're getting this. Everybody's getting an error? Good. Why are we getting an error? Now this is going to be a little bit, we have to deal with that 0. The problem with what just happened, and I want to make sure we can see this right now. Which I don't think we can right now. No, we can't. The problem is, when you look at the graph, go ahead and quit. Look back at your graph. Go ahead, Gabe.
Is it because we have 0 as a data point?
Which 0? The X or the Y? There's 2 zeros. There's a 0 in the first X and there's a 0 in the last Y.
The last Y.
Y is the last Y the problem.
If you keep cutting everything in half, it will never reach 0.
That's the problem with exponential regressions when you have data that ends in a 0. Technically speaking, when you're dropping by half, will you ever touch this x-axis? No, you'll never touch the x-axis. It becomes what's called asymptotic. Now, we got to 0 heads. So when you run exponential regressions, the only thing you have to remember for the regressions, you can't have the last y equal to 0. So just pull that guy out. Pull that data point out. It's going to hang up the regression calculator. So go back to your data. Go back to your data and yard out 6 and yard out 0. Yard out 6 and yard out 0. Cool? And if you do this, you now don't have the problem of the half 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 going to 0, which it never can go. Now run her again. Now run it again. Calc, Expreg, stick it in Y1. Check out what you get. Check out what you get. This is going to look a little bit squirrely at first. I get y equals a, little a, times b caret x. I know. We got to figure this out.
I have a question.
What's the matter?
Should deleting be as simple as putting my cursor over the number and hitting clear?
Hit
No,
delete.
Hit delete.
Hit delete, not clear. Sorry, yes, this is...
Where's delete?
It's right a couple above stat, or one above stat. See the stat button? DEL? No problem. I forgot to mention that. The TI is full of bugs, as we know. Clear clears the entire list, and delete clears one element at a time. My apologies. My apologies. And again, I apologize for this because when I used to teach Math 95, which I taught for years and years and years, we were using these every single day, doing stuff just like this every single day, and I don't think everybody that teaches Math 95 is like that. I apologize. I make the assumption everybody taught 95 like I did, which was basically TI-centric, and it sounds like that wasn't the case. So I apologize for skipping things like that. Cool. But again, if you ever need it, and I know it doesn't help in class when you feel like you're trying to keep up, that little booklet's got all this stuff in there about how to remove an individual element and things like that. Okay. Now, look at this. What does this caret mean right here? That's the power. So what you're seeing when you see this equation, y equals a times b to the x, is y equals a, which is 39 points, so I'm going to call it 39, times b, I'm going to round that to 0.5. Well, what the hell, we'll call it 0.48. To the x power. Let's figure out why, when we press graph, this thing looks so amazingly beautiful with our data. Look at that. It almost hits the data points perfectly. Almost perfectly. Not perfectly, but almost perfectly. Now, it looks perfect, doesn't it? But we know it can't be perfect. And why is it not perfect? How do we know it's not perfect?
There's still yeah.
What's that? What should that be? Shouldn't that be 38? It's saying it's 39. Now, why should that be 38? How are they getting 39? How are they getting 39? Here we have to call back to our old algebra skills. Ready for this? We're going to use our table. Okay, you've got your equation in y1. Here's the messiness of the equation. Just leave that there. That's totally fine. Go to your table. Second graph. Right now you should have a whole bunch of stuff in it. I'm going to press delete. Press delete a bunch of times. Get rid of all that stuff. Okay. We know that on average, when we started our experiment, there were 38 of us that had coins in our hands. But the TI thinks when x equals 0, that there were 39.2 of us. Why is there a difference between what actually happened and what happened here? Ben, go ahead.
Because it still goes up.
Right. It's what kind of fit is this? Best fit. What kind of fit is it not? Perfect fit. It's a best fit, not a perfect fit. It fits as best as it can for an exponential model. So I'm okay with that. After we flip one time, on average, we got 20. Our best fit predicts 18.7. Echo predicted 19. These are all pretty close to what the actual data showed. After we flipped twice, the model predicts 9. We saw 9. Echo predicted 9.5. You see what's happening here, friends? You see what's happening? We're actually getting, this is agreeing pretty well with what we saw in class. After three flips, it predicts 4.3. We saw 4. After 5 flips, I skipped 4. After 4 flips, it predicts 2.03. We
Sean, I
saw
have to
2.
stop you. I'm sorry. How did you get to the x and the y1?
Same as we did last week. Second graph.
Second graph.
Second graph is your table. When you have x's and need y's. Yeah, when you have x's and need y's, we're going to use our table. So what we're seeing here is this is the model where x is the number of flips and y is the heads remaining. You now have a model, heads remaining. You now have a model, an equation that will govern when certain things will happen. Like, for example, how many times do we have to flip, essentially, until nobody has any heads left? How many times do we have to flip? Now, that's a tough question to answer because, as Gabe said, it can't zero out. But it can get down close to 0, which is essentially what this model says. Watch this. Keep flipping. Flip 5 times. According to this, we should have 1 head left, which we did after 5 flips. Flip a 6th time. It's now at 0.46, which rounds down to 0. And that's when we ran out of heads. So, it's the best fit equation. Take a look, friends. Take a look. The 39 is the best fit. What was the perfect fit? What would that number have been? 38. But we got 39. That's the best fit. And what should this number have been right here?
0.
What should this number have been? You guys said it earlier today. It should be a half in a perfect world, shouldn't it? It should be a half. Remember what we talked about? An exponential is repeated multiplication of a factor. The repeated multiplication that's happening is repeatedly multiplying by 0.48. I'm calling on some old algebra here. Let's come over here and show you what I'm talking about. Actually, let's go here. We're done with linear. Gabe, go ahead.
What happens if you put in the perfect equation?
What there is no perfect for. Oh, you mean the point? Good, good. Let's do that in a minute. But before we do that, Gabe, I want to make sure. I think that x in the variable is throwing people for a loop, and I want to revisit that.
Can I ask you real quick?
Yeah.
My X column in my table is, I can't get to the top to delete it. It's like going forever and ever.
Second window, set independent to ask, not auto. That'll let you get in there and mess with it. Yep. The problem is we all changed that 2 weeks ago, but then it's easy to get in there and change it back. So don't change it back. Always leave it on auto or on ask, and that way you don't have to worry about it anymore.
Thank you.
Gabe, I want to come back to that point. It's a very, very good point. But I want to compare and contrast it with the algebra of what's going on. Because if we do it without the algebra, it's going to be more mysterious, I think. I think the fact that that variable is in the exponent is a little bit upsetting for people. So what I want to do is I want to look at what this means. What does 39 times 0.48 to the x, what does that actually imply? Let's go through, kind of like this, that equation being used over and over and over and over again. So, when x equals 0, what's y going to be? Well, according to this, it's 39 times 0.48 to the 0th power. Now, order of operations says what has to happen first, multiplication or exponents. Good. So the first thing we got to do is 0.48 to the 0 power. What's 0.48 to the 0 power? Oh, God. I need to have way more voices than one knowing this. What's 0.48 to the 0 power? It's 1. Anything to the 0 power, I should take that back. Any non-negative number to the 0 power equals 1. So this whole thing here equals 1. So it's just equal to 39. It's just equal to 39. I'm rounding these off, by the way. I'm rounding this off. Okay. How about when x equals 1? How many heads should remain? Well, according to our model, it should be 39 times 0.48 to the first power. Well, what's 0.48 to the first power? 0.48. So it's essentially 39 times 0.48, which is essentially half of 39. Now you can see it right here. He's calling that 18.7. I'm going to call that 19 just to round it off. What happens when we flip a second time? 2. The model says it's 39 times 0.48 squared. But I want you to remember what 0.48 squared means. What does 0.48 squared mean? It means 0.48 times 0.48. So what this means is it's 39 times the 4800ths times the 4800ths again. Now, some of that looks familiar, doesn't it? This part that's right here is the part that was up here. So what you're doing is you're applying the constant multiple of 0.48 to the previous term. Does that make sense? Yes, you're doing 0.48 times 0.48, but the previous term had 1.48. Now you're applying a second one. So you're satisfying that definition of exponential with a constant multiple. So once again, you've taken the previous y value, multiplied it again by the same multiple, 0.48, and you've knocked it down essentially by a half again. This is essentially 9 at this point. And you keep going, and you keep going, and you keep going. 3, it's 39 times 0.48 cubed, which by the definition of cubed, what's cubed again? Using the factor 3 times. So it's 39 times 0.48 times 0.48 times 0.48. Now some of that should look familiar from the previous line, right? 39 times 0.48 times 0.48. That's what we did in the previous line. So you're taking the previous line and multiplying it by 0.48 again. A constant multiple of 0.48. Constant multiple of 0.48. And that comes up being roughly half of that, about 4.5. So, what we got to look for to recognize exponential data is a couple things. There's a visual clue and there's a numerical clue. I think you guys nailed the visual clue. Is this believable? You see what's going on here? When you break it down. Gabe, I've not forgotten your question. We're going to get back to it in a second, I promise you. This continues. If it goes to the 4 flips, 4th power, which means 1 more multiplication of 0.48. 5th power, 5 flips, 1 more multiplication of 0.48. So remember, I've erased it now because I needed more board space. With linear modeling, it was a constant first difference. Quadratic was a constant second difference. What's the constant with exponential modeling? A constant multiplication, if you will, a first product. There's a first product that's constant, not a first difference. A first difference would be an addition or subtraction. It's almost like a first product or a first quotient. So for exponential modeling, you can look for a constant first